In this video, we'll be covering the two topics, which is the Erlang or also called as gamma noise, and also we'll be covering over here exponential noise, which is nothing but a special case of Erlang or gamma noise, right? So again, the things we need to study is the PDFs, the graph, the mean and the variance, whose link will be given in the description below, the step by step for all the noises, right? I won't repeat in the other videos, so just go and check the link if you want to see stepwise mean and variance calculation, and at last we'll see the certain characteristics of the noise, right? So the PDF of the Erlang noise is given by this, that is P of Z is equals to a to the power b. Okay, now how to remember it? Many a times we are able to memorize a into e to the power minus az, right? Because that's exponential and that's easy to learn, that is a into e to the power minus az. But this is the special case of Erlang when we have b is equals to 1, right? So just try and put b equals to 1. So this will be 1 minus 1, 0. Anything to the power 0 is 1. So this whole term, okay, just let me show you, right? So here when you put b is equals to 1, so this is gonna be 1 minus 1, which is 0. So this whole term will be neglected. Here also it will be 1, so just leave it. So here will be 1 minus 1, which is 0. So 0 factorial is what? 1. So you'll be just left with a into e to the power minus az. That's how you'll be getting the exponential function, right? So if I talk about, but that was how we did the exponential noise. But we have to do now what? The Erlang noise. So how we can remember is a to the power b into a to the power minus az, right? So a to the power b into a to the power minus az, that will be very easily memorable. And then we have z to the power b minus 1 divided by b minus 1 factorial for z greater than equals to 0 and for z less than 0, which is again evident from the graph that we have for less than equals to 0, there is nothing, but for greater than equals to 0, this is the distribution it follows. And what I said in the noise models video, that this is also somewhat like relay, right? What was relay? Relay was like here you had something like Gaussian and here you had something like steeper one. But what is the speciality of the Erlang or the gamma noise? It's that here, if you see, at value z is equals to 0, that is at intensity at the gray level, z represents a gray level, right? So at that equals to 0, the p of z has certain value. It's not 0, right? Now, one special thing, right? Just remember for z is equals to 0. When we'll be doing the characteristics, I'll be asking you that, okay, what does this z greater than equals to 0 means? Like, what is special in Erlang noise? We have done the Gaussian noise, we have done the uniform noise. Uh, Now, what is this z greater than equals to 0? Does it imply something? We'll see in a minute, right? Now, the maximum P of Z we obtain at this point, right? Where my Z is B minus 1 by A. And corresponding to B minus 1 by A, the value of P of Z is this whole term. Now, how we got this whole term? We simply put Z equals to B minus 1 by A into this formula. And here it's step by step given to you that how you'll get this expression. So you can pause the video and see that how we obtained it. Cool. And the mean is b by a, the variance is b by a square. Now what are the restrictions on this b and a, right? The thing is that the parameters, the a is greater than 0 and b is a positive integer. Positive integer also means that b is greater than 0. So you can just say that for the Erlang noise, you're going to consider a greater than 0 and also b greater than 0, because positive integer also implies b greater than 0. So this is the formula you have, that is a to the power b, z to the power b minus 1 into e to the power minus az divided by b minus 1 factorial. And the parameters a and b are greater than 0, and this is the mean and variance over there. And this is how we obtain the graph. So there's nothing much special to talk about Erlang, because you can see that it's quite a complex function, right? So we don't see it quite often. But what is something amazing is exponential noise. So when I'll be talking about characteristics, you'll be amazed that how in space, even like space, like literally space, like Mars, you can see this exponential noise. So here when you put b equals to 1, which is a special case of Erlang, you'll get a into e to the power minus z. So the mean and the variance are given over here. And you definitely, because here b is equals to 1, so restrictions used to be a greater than 0 and b greater than 0. So here you just have one restriction, which is a greater than 0, because b is equals to 1 is fixed over here. And this is the graph which we'll be getting, right? So I said now that there is something about z greater than equals to 0. That is this thing, that there is no negative value of noise. Like we have been all talking about that noise is a random number, and if you remember, I said, okay, name any random number. You said 7, you said 11. I said, what if minus 8? Minus 8 can be also be there. And we have seen in the previous, like Gaussian and uniform, that it just depends upon a, and there was no restriction on a, right? It can be anything. Like we have also done Rayleigh, it was just A. There was no restriction on A. There can be anything. You also did Gaussian. We also did uniform. Right. So there wasn't anything like that. But here you can see in exponential and Erlang that you can't have any negative values of noise. So when you are doing numericals, mistakenly you get the negative value, it means that that is wrong. So exponential noise, there are no negative values of noise. This is something which you need to know. Now, this is also seen in quantization. Now, remember which other noise was appearing while quantization? Just remember. Firstly, we did uniform only. It appeared during the process of quantization, right? So, now I was saying something related to space, right? Actually, this is something which appears in error of predictive coding. So what do you mean by error of predictive coding? Generally, what happens that supposedly this is my image, which is 3 cross 3 image, right? Just for the understanding purpose, I have taken such a small image, and I have colored these pixels as pink because I'm assuming that the intensity values of these pink pixels are known to me, and this is unknown, and I want to predict this value. So depending upon the neighborhood, definitely I can predict this value, right? Because some we have generally the images of like 300 cross 300, 5 and 2 cross 300, so they are large ones. So what happens is that we can very easily predict the value of the central pixel on the basis of neighborhood, but definitely we won't be able to produce a very perfect value. What we may do is that we can pick out the median, or we can put the average of all the pink values over here, right? So we may adopt various techniques. So during that, exponential model comes into picture during the era of predictive coding, and you would be amazed to know that even the Mars rover uses it. Like that's how prominent these things are. So that's all for now. Thanks a lot.